Live from Earth, it's Space Radio. This is Paul Sutter, and coming up, we're talking about Enceladus has stretch marks, but it's still beautiful. And of course, taking listener questions about all things in the universe, because that's what this show is about. We record every Thursday at 8 p.m. Eastern, and you can follow along online or leave a voicemail at spaceradioshow.com. And in today's Blue Shift, I'll be talking about blind alleys are for winners. But first, the news. Hello, Space Cadets. Welcome to Space Radio. I'm Paul Sutter, astrophysicist at Ohio State and the Flatiron Institute. And for the next half hour, your agent to the stars. We've got an exciting show for you today where we talk about space, astronomy, astrophysics, rocketry. If it's above the Earth's atmosphere, it's in this show's universe. This show lives on listener questions. We record every Thursday at 8 p.m. Eastern here in Spaceman Studios in New York City. So leave a voicemail at spaceradioshow.com to get yourself on the air. You can also follow along with our Space Cadets on our live streams, tuning in live from around the world, including but not limited to, what is this word? Wassail, England? I think you're just making things up. Brighton, UK, London, UK, Washington, D.C., Austin, Texas, Pell City, Alabama, Chicago, Illinois, L.A., California, and Ashburton, New Zealand. Seriously, folks, I've only prepped 10 minutes of show material tops, so get those calls in. Hey, Space Cadets, welcome to my ski lodge in my mountain chalet where we're doing this show today. Oh, I missed you, Paranor. You're up in Canada. The frozen tundra. New Orleans. Oh, Helios, welcome aboard. All of you. We've got good cheese for you guys today. If anyone can guess, it's a Dutch cheese. If you can guess, you win a prize. What is the prize? The satisfaction of correctly guessing today's cheese. Thank you, of course, Nancy, for wrangling the Space Cadets. We have so much cool news today. So many questions. Got lots of voicemails. I love it. Twitch, lighten up. I love it. Send those questions in. We'll have a chat. From Brexited UK. That is not going to be my debate. I'm not taking part in that. I'm just going to talk about above the Earth's atmosphere. So unless Brexit is leaving the Earth, unless England is leaving the Earth, it's just I'm not even doing that. Not even going there. All right, but there's some really cool, some news. So let's do it. Before I start taking calls, I want to share some interesting bits of news I caught recently. And what really caught my eye, there's always spacey stuff. There's always launches and rockets going on. But I figured it's been a while since we've had a planetary story, a good old-fashioned planetary science, astronomy. And I've caught this interesting bit of news about the moon Enceladus. Enceladus is a tiny little moon of Saturn. And Enceladus is one of these worlds that you would normally just completely overlook. Like, who cares about Enceladus? It's, another little rinky-dink icy moon of an outer world. Dime a dozen. We've got 5,000 of them or something. So just move on by. Let's go somewhere interesting. But Enceladus has a secret. You see, it is icy, but underneath that ice is a liquid water ocean that we're pretty sure covers the entire world. Like, there's probably more liquid water on Enceladus than there is on the Earth. And so that makes it interesting. And we know that Enceladus has liquid water oceans because sometimes the liquid water squirts out into space. There are these cracks, these fissures near the South Pole, and they open up. This is one of my favorite words in all of astronomy. It's called a cryovolcano. It's a volcano that's made of ice. And instead of spitting out magma, it spits out liquid water. And we can see it. We have literal pictures of jets of water squirting out of the South Pole of Enceladus. But what's also very, very interesting about Enceladus is that there are these cracks in the ice. But not just one, there's a few of them, and they're spaced about 22 miles apart. And they run in parallel, and they cover a good chunk of the southern hemisphere near the South Pole. It's from these cracks that the water squirts out, but why does Enceladus have these cracks? They're called tiger stripes, like stretch marky things, I guess, but like it's so fascinating because whenever nature presents us with something like this, we immediately go, why? Why does Enceladus have these stripes? And researchers had long thought you can get at least one fissure at the South Pole. At the South Pole, the ice is thinnest, and it can also cool off very, very easily at the South Pole. And so you can get a buildup of ice in one particular region, and that puts a lot of stress on it. The liquid water ocean underneath it can't squeeze down anymore. And so to relieve that tension, you get a big crack. Well, that's one fissure, but why does Enceladus have multiple fissures, and why are they equally separated? Well, some researchers started playing some numbers games, started doing some simulations, and they found that on Enceladus, the formation of one fissure starts letting liquid water seep out. The liquid water seeps out, moves down the slopes, and then starts building up parallel to the crack, which builds up ice there, which builds up the pressure, which causes another crack, which causes more water to seep out, which allows that water to move further down, then crack again and again and again. So as soon as one fissure cracks open, you get parallel ones to it opening up, and then parallel to that, and then parallel to that spreading out. And they think this only happened on Enceladus because, like most things, Enceladus just happened to have the right set of conditions to allow this to happen. The other icy moons in the outer worlds don't have the right temperatures, don't have the right thickness of ice, just don't have the right properties to allow these fissures to even appear in the first place. So Enceladus appears to just be a special case. Now, are there space whales swimming around in the ocean of Enceladus? I sure hope so. That's the latest and greatest when it comes to space, but it's time to have a conversation. That's fun. Oh, thank you, Scott. I'm glad you like the background at my chalet. It's in the non-Swiss Alps. It's the other Alps. It's different. It's different. All right, I've got two voicemails, and I think I'm going to do both of them because remember last week it was all Space Cadets all the time. I didn't do any voicemails, so I think the voicemails deserve some love, but don't worry, Space Cadets, keep those questions coming, and we will get to all of them. That's not true. I never get to all of them. Well, no, one show I did. One show I was able to get to all of the questions, and I felt very proud of myself. I was very, very happy. All right. Is there heat there, Constellation Pegasus? Yes, there is heat. Tidal heating from orbiting Saturn, it keeps the interior of Enceladus warm, and that's what makes it so liquid. All right. You guys ready to go? Let's get these callers in. We've got a voicemail ready to go, so Greg, play the tape.
Was on the moon. What are the feature things are on the moon?
Oh, this is a great question. I love it, asking about features on the moon. Just what are they? And the moon is something we take for granted, right? Because we're always staring at it. We're always looking at it. It's almost always up there in the sky. And of course, we've named the different craters and regions, but until we actually went there and started digging up moon rocks and bringing them back to Earth, we didn't know really what was going on. Why did the moon have all these different features? One of the main features you see on the moon are obviously the craters. These are leftovers from comet and asteroid impacts, most of them happening about 3.5 to 4 billion years ago during a period in the formation of the solar system that we call the late heavy bombardment. The craters appear to be in what we call highlands of the moon. These are older regions of the moon that have been uplifted from past magma and from past lava flows and volcanic activity. That's the word I was looking for, volcanic activity. Those appear to be the oldest regions. And then there's these long, big, darkish regions that we call the mare, which is Latin for seas. They are not actually oceans. They're just moon rock that is slightly darker. We believe these are outflows from massive volcanic eruptions, like giant. You ever have that pimple on your head that is just like screaming at you? That is like a volcano on the moon when it was 4 billion years ago. These have massive outflows, smoothed out big regions of the moon's surface, and then cooled down as a lake, as a magma lake. So they were an ocean at one time, an ocean of rock, and now they're just regular normal rock. The material on the moon, the actual rocks and dust, is something called regolith, and it's a mixture of all the other kinds of things that you might find on Earth: silicates, carbons, calciums, magnesiums, little bits of oxygen here and there, all the usual stuff. But that's the side that faces us. The far side of the moon, the side of the moon that always points away from the Earth, is a very different story. It doesn't have a lot of mare. It's almost entirely cratered. And how the moon got this difference between the near side and far side, we know it has something to do with the gravitational interactions with the Earth. But that said, there's a lot to learn. We don't know as much about the far side of the moon as we do the near side because, it's harder to get there. The Chinese do have a lander. The Chang'e lander is roving around the backside of the moon, sending back data. So more and more as the years go by, we learn more and more about the far side of the moon. And the far side of the moon obviously contains, because it has so many more craters, it obviously contains some record of what was going down in the solar system long ago, more so than the near side does. Excellent question. I'm going to jump right into another question. I know I don't have enough time to answer it, but that's okay. Greg, play the tape.
Hey Paul, how's it going? Hey, I've got a question about quantum mechanics and the vibrations, the jigglings of these fundamental particles. Do the particles vibrate in quantums of time? Do they speed up or slow down in relation to a quantum of time, or are they just constantly moving in a more analog kind of way? Does heat also change these vibrations in the way that heat changes the movement of an electron around its nucleus? Cool. Hey, thanks very much for this, and catch you later.
Oh, thank you, Campbell, for this wonderful question about atoms and particles wiggling around. I love it. I am going to answer it after the break. So if you want to know how particles wiggle, then you need to stay tuned. We are going to take a quick break. Don't forget to leave a voicemail, just like Campbell did, to join the conversation, or you can catch the live streams with the other lovely space cadets over on YouTube and Twitch. Visit spaceradioshow.com for all the links. I'm Paul Sutter. This is Space Radio, and this show is brought to you by you. Go to patreon.com/PMSutter to learn how you can support the show, and we'll see you after the break. All right. Space squids. Okay, fair. Maybe space squids. You're right. You know what, Larry? That is a very, very excellent point. that space whales on Europa, whales are descended from land living creatures, so they need to come on the land, evolve for a while, be like some sort of dog or bear like thing, and then go back into the water and become whales. So we need a different lineage. I can't say space whales because they can't access the surface of Europa and evolve on the land for a while. So you're right. Maybe it's space squids. Maybe it's space octopodes. Maybe it's space ichthyosaurs. Can we have that? Did ichthyosaurs evolve completely in the water? I hope so. So that Enceladus can have space ichthyosaurs. Can this be a thing? Oh, Constellation Pegasus, the goo that the Chinese lander found, it was nothing. There was no goo. Are we still saying fake news? Because that was fake news. All right. We got Cosmic asking, what would you see about in a void? Very cool. How far would a proton be from us? And how the speed of light is constant throughout all the universe. When tripped to one place, it doesn't make any sense. Very cool questions. Plenty of questions to get us through this 9-minute segment. You guys ready? Moon sharks on Enceladus? No, get out. It is Enceladasian ichthyosaurs. Is that going to be the title of the show? Enceladasian ichthyosaurs. In lots of bioluminescence, maybe. Oh, I can take my earpiece out because no more voicemails. All right, you guys ready? Let's do it. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. I'm in the middle of answering a voicemail question. And remember, you can join the conversation by leaving your own voicemail or by following the live streams. Go to spaceradioshow.com for the links. Now, getting to Campbell's questions about particles vibrating. Now, there's two different senses that we use to describe particle motion and particle vibration. One is in the concept of trying to understand heat and temperature. If you have a box of particles, those particles are just moving around because what else are they going to do? They're not going to stand there. They're just going to bounce around. They'll bounce off of each other. They'll bounce off the walls of the box. And if you raise the temperature, what you're really doing is giving more energy to these particles so that they can bounce around even more. And you will feel this because the particles will be hitting you more often, which you interpret as heat. They'll be hitting the walls of the container more often, which you will interpret as pressure. So particle motion, the kinetic energy of individual particles all together inside of a box is what we call pressure and temperature and entropy. Now there's another sense that particles wiggle, and this is through quantum mechanics, and specifically something called quantum field theory. Quantum field theory is how we describe 3 of the 4 forces of nature, sorry gravity, and how we describe particle interactions. It's just how things work at a very fundamental level. And at a very fundamental level, we don't look at the world through the lens of particles. We look at it through something called the field. We look at something called the quantum field, hence the name quantum field theory. In quantum field theory, every single particle that you know of, every kind of particle like the electron, like the top quark, like the neutrino, has an associated field that soaks all of space-time. I like to imagine olive oil soaking a piece of bread because I really like food metaphors. And these fields themselves vibrate. They are never quite at rest. They're always jiggling and jittering and shaking and quaking just a little bit. This is just their nature. This is their quantum nature. And if you take a field in a particular location and you grab it and you shake it enough, if you give it enough energy, then it becomes a particle. A particle appears in that region of space. What we see as particles are really little local wiggles in a much larger field. So that's the quantum mechanical description of basically reality. And that's where we get a sense of particles wiggling. The particles themselves don't quantum mechanically wiggle, but the field that soaks all of space-time does. And it's through that we understand it. Excellent question, Campbell. Now I gotta give the Space Cadets some love because they love me so much. I'm pretty sure, right, guys? Okay, never mind. Cosmic over on YouTube is asking, what would one see from the middle of a void between superclusters of galaxies? Would you see any light at all? Now, a void, we got to talk about large scale structure. We got to talk about the very largest things in the universe. These are scales where you zoom out and away from solar systems, from star clusters. You zoom out away from even entire galaxies. And when you zoom out all the way back, like super macro wide lens, where you're looking at scales so big that individual galaxies are just tiny points of light, hundreds of billions of stars, just a tiny little point of light, you see something that we call the large scale structure of the universe. We call it the cosmic web. There are long strings and filaments of galaxies arranged in what we call superclusters. And between them are vast expanses of almost absolute nothing that we call the voids. Let's say that we were to take our Milky Way galaxy and plop it right down in the middle of a void. How would our night sky change? The answer is our night sky would hardly change at all. Because the stars you can actually pick out with the naked eye in the night sky are all within like 1,000 light years. Compared that to the 100,000 light years it takes to get across the Milky Way, we're looking at some tiny, tiny little bubble around us that defines our night sky. All the stars you see, these are the giant stars. These are blue giants. These are red giants. This is not extragalactic. These are our local neighborhood. This is in our little town, all right? In our little suburb, our little neighborhood of a city. It's not even the city of the Milky Way itself. The only thing that you would really know was different was that the Andromeda Galaxy would be missing. Andromeda Galaxy is our neighboring galaxy, 2.5 million light years away. Andromeda Galaxy is the furthest thing you can see with the naked eye. It's the accumulated light of 1 trillion stars. If we were in the middle of a void, you wouldn't be able to see any nearby galaxies because they would be hundreds of millions of light years away. They would be too far away to pick out with the naked eye. But as soon as you pop open a telescope, you get to see the universe this exact same way that we see the universe. You would find you wouldn't have a lot of neighbors. And so maybe you'd give up before you built sensitive enough telescopes to spot other galaxies, but you'd probably keep trying, and then you would be in for a surprise once you found that the universe was filled with galaxies. I mean, to be fair, it was a surprise for us too when we found out that the universe was filled with galaxies, and we're right in the middle of a supercluster. So when it comes to backyard astronomy, nighttime, nothing much is going to change. But I should say a Milky Way galaxy isn't ever going to appear inside of a void. There isn't enough stuff inside of a void to actually build a galaxy as big as the Milky Way. So what we know of as the night sky wouldn't naturally evolve inside of a void. So, two ways to look at it as usual. Over on YouTube, we got a question here. I don't understand how we conclude that the speed of light is constant throughout the entire universe when we've only checked in one place. I mean, yes, we've done laboratory experiments here on Earth, but we are very interested in the constancy of the speed of light because realizing that the speed of light is constant was a cornerstone in developing special relativity. And special relativity itself is the most well-tested theory in all of physics. It probably in all of science is tested every single second of every single day. And so if, the speed of light really did change, we would notice. But this opens up a larger question of how do we really know that physics is really universal? Is the speed of light the same over in the Andromeda Galaxy, in the edge of the universe? Has the speed of light been the same since the Big Bang? That's a good question, and as far as we can tell, it is. And we can test this by looking at things. If you look at an object and try to understand its physics, and try to explain, like, okay, maybe the speed of light has changed, that's a prediction. That leads to testable predictions. You say, oh, if the speed of light were different in the early universe, then say something like the cosmic microwave background ought to look different. And it doesn't. And so, as far as we can tell, the speed of light is the same. Or if you look at a distant galaxy and say, I wonder if the speed of light is different over there, then that is a prediction. That leads to predictions that you can make. And you test those predictions, and you know what? As far as we can tell, the speed of light is the speed of light. We're almost out of time today on Space Radio, but before we go, it's time for the Blue Shift. Fun questions. I can't resist talking about space whales, but maybe I should talk about blind alleys. Okay. I'm Paul Sutter, and you're listening to the Blue Shift. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get a little bit closer to you. Now, I wanted to talk about blind alleys and how powerful blind alleys are and how they're actually required. In order to get good science, you need to have blind alleys, because the whole point of science is that you don't know what you're going to get. Because if you already knew, you wouldn't have to do the science. Science is about investigating. Science is about exploring. Science is about uncovering new things. And so, there's going to be a lot of promising research that goes nowhere. And so, but that doesn't mean you don't learn anything from a blind alley. And I just realized, thanks to the space cadets, that I've been going down a blind alley. For years now, I've been joking about the space whales in our solar system of Enceladus, Europa, maybe even Pluto and Titan and Ganymede. They have these subsurface oceans, these oceans that never see daylight at all, but they're massive amounts of liquid water. And so I like to envision, just in my own private fantasy world, space whales like creatures swimming around. But Larry, over on the YouTube chat, one of the space cadets pointed out that whales evolved from mammals. They are mammals. They evolved from land-dwelling creatures. Enceladus and Europa, these worlds are completely 100% encased in ice, which means there's no evolution on land. It's only going to be in the water. I've been going down this blind alley envisioning space whales, and it's simply not going to happen. I can only have creatures that evolved completely in the water. So I'm going with, and also whales breathe air. Okay, fine. I get it. Thank you, Sybil, for also pointing that out. Blind alley for multiple reasons. I'm going to go with space ichthyosaurs. Or plesiosaurs. I'll take either one of them. Either the long neck ones or like the big jawy ones. Space ichthyosaurs or space plesiosaurs swimming around the oceans of Europa or Enceladus. That is what I want for Christmas. I could also get an octopus. And unfortunately, this broadcast is almost done. Thank you for joining me on this voyage of space radio. Once again, I'm Paul Sutter, and this show is brought to you by you. Visit patreon.com/pmsutter to learn how you can contribute. Thanks to Greg Moebius for producing, Nancy Graziano for wrangling the Space Cadets, and all the fine crew at WCBE Radio in Columbus for making this show possible. Catch the live stream every Thursday at 8 p.m. Eastern. Visit spaceradioshow.com for more info, links to the live stream locations, and the episode archive. You can also follow me directly on Twitter and Facebook. My name is at Paul Matt Sutter. And of course, thanks again, Space Cadets, for listening. See you next week. And remember, science is for sharing. End of transmission. Okay, Larry's pointing out that dinosaurs are air breathers too, but plesiosaurs and ichthyosaurs are not dinosaurs. Shoot, do they have gills or do they breathe air? This is gonna be so bad. I need title suggestions, folks. I need title suggestions for today's episode. Space Sharks is, but I want something better. Space Sharks sounds so derivative. Like it's always gonna be sharks. Sharks are always cool. Sharks are always the best. It's just such an easy go-to. Yes, Larry, you are upsetting me because you are not letting me have my space whale fantasies come true, okay? You are a dream crusher. Thankfully, I have some cheese. Oh, yeah. Now, some of you guessed what cheese. You guessed a Dom. No. I don't think I've ever had this cheese before. It's a Leyden cheese. Look at that. With cumin. Look at this lovely guy. Now, I looked up Leyden cheese. It is a cow's milk cheese from Holland. Very, very yummy looking. I think Leyden is almost exclusively made with cumin. Or of the cheeses that include cumin, it is like the number one cheese that you would put cumin in. This is from Kroon. Kroon cheese. This is imported since 1831. So good job making this cheese for almost 200 years. It is a cow's milk cheese. Very high fat content, 30 to 40%, typical. Similar process as Gouda and Edam. Got a nice red wax coating. But you notice the wheels aren't as roundy as they are for the Goudas and the Edam. So there's this rectangular wheel that they go. Look at that. Lovely, lovely. Loads of cumin. Look at that. That is like cumin town in there. So I will take a small slice because I just had dinner, so I don't need a lot of cheese today. I'm just kidding. I'll eat half of this before I go to bed. It's not a problem. I do not have a problem with cheese. Cheese has a problem with me. All right. Look at that lovely. It's got a very nice texture. It's soft but firm. It's pretty supple. It's a very supple cheese, and I love seeing all that cumin. Cumin is one of my favorite herbs. Wow. Unexpected mouthfeel. You know what? I thought it was going to be soft. Just from the texture, like it's very springy. So I thought this was going to be very soft and kind of melty, but it's a little bit dry and crumbly. Here, you can take a look inside. Can you see that? Will the camera focus? Probably not. It's very